In one of the video, this download world soil grid data in R. Here I have got one comment that can you please show us how to extract soil data characteristics using R for a specific GPS location. So here in this video we are going to solve this problem. Suppose we are having some GPS points. For that we will be extracting the soil data from soil grid, and we can do it for our polygon also. Suppose if you want for your country or your state or a watershed, that also we can do. So in this video we are going to see how to do it. So again we will need this library geodata, then Terra and SF. So in the earlier video in which the comment was there, we have used the library soil_world, and here you need to give these arguments like which variable, which depth and which stat, either mean or uncertainty, and these are the description of variables. Suppose you want pH, then pH H2O you have to write. Similarly for sand you have to write sand and silt and clay and others. And this depth, if you are writing 5, means it will be giving the first depth 0 to 5. If you want the second one 5 to 15, then you have to write 15. Similarly 30, 60, 100 and 200. So now see, these two arguments you must write there, variable and depth. Others like stats, by default it will be taking mean, but for this there is no default, so you have to write this. So I am going for soil pH. Here we will be using this function, soil_world_VSI. So variable I have taken pH H2O, means pH of depth 0 to 5 cm. So we will be running these codes. If these libraries are not there, you have to install it. And then this one, it will take some time. So once downloaded, now we are reading our point data. So you have to use function stread. You can also use function from Terra or rasters. So read. So I am reading this point file with point_SF as a name. Then we can plot it. So these are the points, and it is having only ID as a field. So now we will convert this point SF object to a vector, means Terra vect. This function is from Terra. So run here. Now we will be extracting the value. So extracting the value from soil raster. So function is extract from soil raster to points vect. Now you can run it. See the values it has extracted. So it is having ID pH H2O _0 to 5 cm _mean. This is the name of this field. So now we will be combining this soil values, means combining this second field or second column of the soil values to point SF, and while combining we will be naming the field as, suppose, soil_pH and then 5, so that we are aware that this is for 0 to 5 cm depth. So we are adding one field to point SF with the field name is soil_pH 5, and it has the values of soil, second column of the soil pH. So we are selecting all the column of the soil pH. So run it, and then now you can plot. So you will see two values, ID and soil_pH 5. Now you can write it in the name like soil with pH or soil pH 5. This point SF we are writing. So run it. Now you can go to this we have created just now. So you can see here the soil pH 5 we are having. Similarly, now suppose you want to clip or crop your desired raster from soil grid with your polygon. It may be your state, district, or your country, or any watershed, village, any boundary. So in earlier video you have seen that entire global data we were downloading. If you want to download only for your region of interest or area of interest, then how to do that we will see here. So this is my watershed boundary. I can plot it, plot watershed. So this is the watershed boundary. Now again we are going, suppose in this example we are going to download soil organic carbon stock. So this data is having only one depth, 30, means 30 centimeter, 0 to 30 centimeter. So I have written 30 centimeter, and the variable name is OCS in small caps. So same function we will be using. Then you can plot it. So global data is there. Now one more thing, that CRS of this global data in soil grid is having a different projection named interrupted Goudet homolocene projection. This projection system is a composite of two projection systems. One is sinusoidal and second is mole bed projection system, and there is transition around 40 degree 44 minute and 12 seconds both in north and south. And in this they are making some lobes, means interruptions are there, and these lobes are mainly made in the oceans, so that the land mass area is not distorted. Since we are using it in this data in some modeling, land mass area will not be exaggerated, and you will be having minimum distortion in shape also. For this reason, now we have to transform our this watershed boundary to the soil one. So just we will be taking the CRS of the soil and then transforming the watershed with CRS soil, means projection system of soil, and then converting it to vector. So just run it. Now we will be cropping the OCS raster with watershed reprojected and then masking it. Now we are plotting it. See, this is in interrupted Goudet homolocene projection. Again we will be reprojecting it to UTM, since if you want to make it UTM, using function project of Terra, and then you have to just take this object OCS underscore watershed and write the name of projection. So EPSG projection, this 32 represents for UTM, 6 for north hemisphere. If it is south hemisphere, it will be 7, and then 44 means 44 zone. So this data, this area of interest is under UTM 44 north. So EPSG 32 6 4 4 I have written. So I will run it and then plot it. So now you can see differences between the two maps due to projection. Now we can write this UTM projected one by using the right raster function like this. Now we can see here in RTS, this was our watershed and this is the data. Thank you for watching.